Thank you very much for organisers for inviting me. It's a great pleasure to be in LA, particularly given the weather, and the weather at home is pretty miserable, so it's very nice to be here in February. As Maria said, what I'm going to do is to talk to you a little bit about some of the work that we've been doing over the last few years, looking at how we can use mathematical methods to investigate sort of mental health benefits, translational mental health benefits. And the great thing about being at the end in the graveyard shift is that I get to sort of like fill in my talk with lots of things that I've heard over the last 4 days. So it's been really fantastic to actually being able to think about some of the things we've been doing and put it into some sort of context of this meeting, which, as I said, has been absolutely fantastic. So I'm going to start by giving you sort of, and this is not new because actually everybody else has already talked about this, the way we think about this sort of thing. I'm going to give you a little bit of a background to the way that we think about hierarchies in cognition and the way that we're going to sort of approach that. And I'm going to give you sort of two examples. The main part of my talk is going to be on thinking about mood and bipolar disorder, and the sort of towards the end I'm going to sort of present some newer stuff that we've been thinking about on trauma memory and PTSD. So the background is actually just to illustrate that actually I don't do this alone. In fact, there's a huge number of people involved in this, and particularly my principal collaborator on this is Emily Holmes. Emily was in Oxford for a long time, based in psychiatry with John Geddes and Guy Goodwin. She's now based in the Uppsala University in the Karolinska in Sweden. And Emily runs a huge team of people all below, some of who I put on here, just to remind me that I'm actually presenting some of their work. She runs this huge team of people thinking about how we can use sort of mechanistic approaches in thinking in understanding mental health disorders, particularly based around imagery, and I'll get into a little bit about that through the talk. So yeah, these sort of people, sort of Ali and Kate, I'll talk about some of the PTSD stuff. Sophie and Fiona involved in some of the bipolar stuff. And there's a bunch of people who support us throughout all of this, basically, particularly me, supported by the Royal Society in the UK. So the conceptual basis that we think about, as I said, is not new. It's been presented lots of times over the last few days, and this idea there's a sort of hierarchy. And we're approaching this, we're sort of like taking this as the sort of like the starting point in the way that we're developing these mathematical approaches to understanding mental health disorders. So it's going to start at this particular point, using mood and this idea of a state of mind, but what we really want to be able to do is to sort of scale down through these things. And we've heard lots of things about that over the last few days. So on Tuesday, lots of stuff about brain oscillations. Yesterday, really cool talks about the way in which we can build really complex models to understand neuron firing patterns and coupled neuron firing patterns. So some really cool stuff. And what we want to be able to do is to start at one of these points and being able to scale up or scale down. And as I said, and what we're trying to do is to understand cognition in some broad context. And we're going to, as I said, we're going to start with mood, and we're going to try and link that to brain oscillation, some sort of putative or tacit way of which we believe might explain brain oscillations, and thinking about how we can sort of scale down to neuron dynamics. So I just got to get into some of the details, basically. So we're going to start by thinking about mood and bipolar disorder. Daniel yesterday presented a really nice piece of work on sort of bipolar disorder and his reinforcement models, which was really cool. And I don't need to say too much more about what this is, but this is some sort of statistics of a bipolar disorder characterized by swings in depression and mania. And as was emphasized yesterday, mania isn't necessarily a happy state, it's a more of an elated state. So thinking about how we approach that. And one of the things that's really critical here is that episodes of depression and mania in bipolar can be quite rare, but actually there's lots of sort of like variation that may happen between these episodes, these episodes of mania or depression. And Emily and her team have been using that as a target for treatment, using that as a way, using that that mood variation, which may be more of a morbidity, and in affecting people's behaviours. So we saw this is just a schematic. We've got sort of mood against time, and we sort of have a manic episode and a depressed episode, and it's these sorts of things here that we may be more interested in thinking about as targets for treatment intervention. And the way that we might approach that is by having longitudinal studies, and I'm interested in this from the dynamics perspective, from thinking about how do these things change over time, how does mental health state change over time. And this is just one of the classics, one of the sort of representative sort of time series that we might have from an individual patient. On the y-axis we have a sort of a scoring system that sort of measures depressed symptomology, so maybe self-reported or clinician reported, and then we have this over time. So, and these are reported, these QIDS scores are reported on a weekly basis over about 4 years for this particular patient. In Oxford, out of psychiatry in Oxford, there's been a long sort of outpatient program called True Colours, where patients have been using cell phones or internet to report their mood on some particular temporal scale, in this case a week, and we can use that huge data set to be able to sort of drill down into some of the dynamics that we are interested in. So some of the things that we're interested in here are basically, as I said, are the sort of these sorts of fluctuations. Some of the things that challenge us in terms of thinking about this is that there are breaks in here, there's some missing values that we may have to deal with, and also the sort of like from a statistics perspective, which I will get into a little bit more, is actually thinking about the way in which we can write down appropriate statistical models to describe these sorts of dynamics. So I'm going to step through this, and I'm going to step through this in terms of thinking about a descriptive approach to those time series, and then to get into some of the mechanisms. So we're going to start with thinking about how can we define sort of appropriate statistical frameworks for these sorts of mood dynamics. And it looks like, so the first piece of work we did looked something like this, where we've got we're writing down a time series model. So we're trying to predict the numbers, the scores in the next time step based on some lagged states of those mood scores in previous time steps. And we heard on Wednesday lots of cool stuff to do with how we might use this as a sort of linear model. And we might be interested in thinking about the significance of those that particular framework, and contrasting that with what Daniel said on Wednesday against the sort of predictive machine learning approach. And actually, I think we have to be careful when we're thinking about how we use these sorts of models and how we contrast those with the sort of machine learning methods. These are predictive models. We're trying to predict the QIDS score in the next time step based on some mechanism, so based on some statistical description. Yes, they're linear, but we don't just pick a single linear model in this case. And we will kind of contrast a whole host of different linear models, or different dynamical models, as we get into the talk, about how they might describe mood variation. So I think it's really important to separate out that actually on the one hand you have maybe having a single hypothesis where you are trying to fit to a particular linear model that has where you care about the significance. But we also want to be critical of that linear model and say, actually, it may not be the best descriptor. We might want to think about other candidate models. So somewhere between that extreme of a single hypothesis testing and at the other end, the machine learning, the hypothesis generating approach, sits in the middle of this, is multimodal comparison. Is being able to take a range of hypotheses and challenge the data with them. And that's predictive. As I said, we are predicting scores from a set of, this case, linear components to describe the dynamics that we see. So I think it's really important that actually we don't just think of these two things as polemics. There's actually a continuum of approaches which have been well used in our inferential statistics over the last 50, 100 years to actually help us understand systems. So this, just again to a bit of the details about this, as I said, these are a set of lagged variables. So we're thinking about how does QIDS score in the previous time step, or 2 time steps back, or 3 time steps back, help us understand QIDS score now. So that's this bit, essentially. This bit tells me there's some error. There's going to be some unexplained variation in that, and I'll get into that in a little bit more. And then this bit tells me that actually what I'm doing is I want the model to be piecewise linear. I want actually to be able to describe those dynamics differently in different parts of, or I could possibly want to describe those dynamics differently in different parts of the time series. So we want to be able to sort of allow that model to have this flexibility to be able to think about things that happen at different points in the time series. The error term is critically important in this, as was emphasized on Wednesday, and as we're all aware, our statistical methodologies are all built around the central limit theorem and all built around this idea that things are normally distributed. Well, unfortunately, scores like this are not going to be normally distributed. Normal distributions go from minus infinity to plus infinity with a sort of like a central tendency around 0. This is bounded. This scoring scheme, this psychological scoring scheme is based out of 16 questions and has a range from 0 to 30. So that's going to constrain the sorts of ways that we want to the way that we want to construct our error terms in these time series models, and that's really important. It's really critical to get that right because these errors are not normally distributed, and we can think of other ways of doing that. And the way that we found that works best is to assume that those errors, and we can show that they're gamma distributed. And a gamma distribution is like a normal distribution, but it's got a little bit more flexibility in it. You can allow that symmetry. You can allow sort of asymmetries in the probability distribution. So it's made up of a shape, or size, shape, and a rate parameter. And we want to be able to sort of use that flexibility in this distribution to describe these sorts of QIDS scores. One of the other things that's really important about time series that I'm just going to labour, because as you might get, I'm quite interested in time series analysis, is that actually we want to have this this might look like a complicated likelihood structure, but it's just made up of one gamma distribution and then a sort of product of a bunch of different gamma, a product of then other gamma distributions. And in time series we really care about the autocorrelation in these time series. So how is a point now affected by a point in a previous time step? And that point now is not going to be independent of what's happened in its past. And in a classic Markovian sense, it might only be dependent, it might just have the history on what was happening in the previous time step. So we need to be able to do that. We need to be able to we need to condition our likelihood on the previous value or the previous values that are in this time series. So that's what this does. It sort of this product term is conditioning a value at a particular point in time based on some previous values. And that works very well from the second point onwards through your time series if you're just looking at one step back. And we have to then think about what we do with the first point in the time series. We might throw it out. We might say, actually, we can't condition a likelihood on that because there's nothing before we started to measure, so we could just throw it out. That means that we lose that information. We may care about that, we may not care about it. It really depends on the longitudinal length of your time series. But there are other things that you can do, and you can condition this on the mean of the time series, or on the mean of the observations from the time series, or you might condition it on something to do with the expected values from the model that you're fitting. It doesn't really matter, but it's really important that we consider the autocorrelation structures in these time series because they matter. And the first piece of work that we did on this, as I said, was pretty descriptive. We took these models, clinicians, there was 23 time series, Guy and John, the psychiatrists we worked with, had separated them out into patients who they perceived or they knew were low risk of bipolar episodes, and those that were more high risk of bipolar episodes. So it's sort of like a split in about half, so 11 and 12 patients into those respective groups. And then we asked basically, how can we describe those time series in that group of patients? So not the individual patients, but on the aggregate. What sort of time series structures best explain those sorts of dynamics? And it turns out that actually these they're called threshold autoregressive models, these piecewise linear models work really well. We want to be able to understand that things happen on different points of the time series, so we can contrast a whole set of different linear models, as I was just explaining. And then we want to say, then we were able to show that actually the structure of patients who were at low risk of bipolar and those that were high risk of bipolar had different structures to the time series. More complex, so taking more structure in the patients with who were high risk. So you needed more information from the time series to be able to predict out what the next QIDS score would actually be. What we've also done is to sort of like, with Emily and her team, is thinking about how we can use these sorts of methods in a more interventionist sort of way. In this study, there were 14 patients as I said, Emily and her team are interested in using cognitive behavioral therapies, but using imagery rather than verbal approaches to be able to treat people with PTSD and bipolar. So the aim of this particular study was to say, let's sort of take a bunch of people who suffer from bipolar into a small scale study and monitor their QIDS score over a period of time. Let them go through the imagery-based treatment, and then let them repeat this scoring over the next tranche of time. So patients came in to clinic, were sort of given briefings on what was to do. We developed mobile phone apps and internet apps where they could report on a daily basis their QIDS score and before and after treatment, and we wanted to then understand using that statistical framework to be able to understand the dynamics that we see. So are they single autoregressive models or these threshold autoregressive models? What are the, sorry, yeah, all good. You can.
It looks like there's a little bit of a phase shift of the model versus the actual observation. Is that typical for these types of models?
Yep, I'll get into. Yep. So I will explain. So what we have is that the black lines are the data, the sort of QIDS scores that we see, and then we want to be able to fit. We want to be able to fit the model, whatever these models are, to the best fitting models to these time series. So one of the things, as I said, that we care about is how to deal with these missing values, and we use a sort of like a mixture of supervised and unsupervised machine learning methods. What we're using here is an expectation maximization method to actually predict over those missing values. So rather than having a supervised machine learning method where we have all the points, we're going to sort of like use the model, and we're going to fit the model over these points, and then we're going to recompute the likelihood and get the best estimate for those missing values. So we do that, and it's a pretty robust method for identifying out where there are missing values. And you're right, Martin. One of the things we then do is we want to assess the goodness of fit of those models, of the best fitting model to the time series. And there are lots of ways of doing that. And the way that we illustrate this is the one step ahead prediction approach. So the idea with the one step ahead prediction approach is that I have my best fitting model, and I use that best fitting model at each point to say what would the next value be. So it looks like it's jigged along that, but it's just that it's just using those one step ahead prediction methods. And then we can do goodness of fit, whatever your favorite goodness of fit method might be, to say how much of that variation is explained by that model. And we can do that for whatever our sets of candidates models are. Or we can use particular weighting methods. We can use an AIC method or an information theoretic criteria method to actually work out how much information is explained by this best fitting model to compare to all the rest of those candidate models that we may select. And that turns out to be a pretty robust way to actually identify the idea that there may be potentially multiple hypotheses just driving these particular dynamics that we see. So So that's really sort of like sort of an illustration of that. We can actually use these. We can use them on the aggregate, and we can actually use these models on, because we have, well, let's say time series. I'm not going to say long time series, but we have time series for each individual patient, where we can then build models that help us understand the dynamics of the individual patient. Yeah. So one of the things we want to be able to do is that we can use those models on the aggregate, as I said, to sort of like separate the clinician determined groups. We can use those particular linear models to understand individual patient variation, and we can make sort of predictions about that. We also want to take sort of some of the things that Martin was talking about yesterday. We actually want to be able to sort of take this idea of being able to make these translational. We want to be able to use these models in a useful way to be able to help patients understand their own dynamics and help clinicians understand how to profile particular patients and determine whether they're at risk of manic or depressed episodes. So what we can do is that we can sort of collapse over those QIDS scores a little bit and think about sort of like determining this sort of like state space in this QIDS score state space using a Markovian framework. So the idea being that now we sort of, with this basically, this is a transition matrix. So I have a probability of staying in a particular state or moving to another state. And what we've done is we've just collapsed over that continuous set of scores and grouped them into 3 bins, essentially 0, 1 to 9, and 1 to 8, and then 9 and above, essentially. And they were sort of like in conversations with Emily and John and Guy, thought to be really good ways in which this being a particularly high QIDS score and high risk of a bipolar episode. So we can build this transition matrix, and what we can do is we can build that very empirically. We can build that from the time series that we can see. We can say, what is your QIDS score now? What is your QIDS score in the next time step? So you can build up the sort of frequency distribution of staying in a 0 state. If you're in a 0 state in the last time step, you can build out the frequency of moving to a score less than 9 or a score greater than 9. So you can build out the structure to this Markov chain. And then what we can do is sort of like lots of machinery associated with Markov chains that we can use. And one of the very simple ones is to work out what is the long-term steady states of being in these bins, basically being in the 0, being in the less than 9 class, or being in the greater or equal to 9 class. So we can use sort of like some of the, as I said, the machinery of Markov chains to work out what the long-term probability of staying in a state would be. And they can look like this. These are sort of quite cool. If you look at them long enough, they do sort of flip back at you, so you get sort of that perception rivalry thing going on. So what we have basically, these little triangles sort of determine what the sort of expected state of a particular patient would be in pre-treatment, and then what their expected state would be post-treatment, essentially. And the sort of like corners of the triangle determine basically these are QIDS. So in the left-hand corner, these are QIDS scores where greater than 9, sort of between 0 and 9, and then 0 basically. So we want everybody to be sort of in this blue state essentially. And you can look at these, and the really cool thing about these is that we can, as you get more information, you can continue to update that transition matrix, and you can continue to update what these sorts of frameworks look like. So you can pick out this particular patient, participant 7. Basically, the size of the blob determines how much frequency, how much sort of probability mass is sat on those points. So this particular patient, there wasn't much change post with the sort of imagery-based intervention. But then you see patients where actually there's sort of like they have QIDS scores that mostly in the high category, and then after treatment they sort of like there are a few more scores that are in the low categories. And you can see sort of like these sorts of shifts basically through this imagery, through this intervention. And there are some people where it actually gets worse. So this person in particular, who sort of had a set of sort of low scores pre-treatment, and then after treatment, it was post-treatment, they were sort of like worse. But that's quite cool. We've been able to actually understand that there's individual patient variation, and being able to quantify that is a pretty nice approach, we thought, and being able to use this simple math to be able to get to something that you can use that you have a snapshot of, and as more information comes in, you can change these sorts of things. You get something that you're able to that patients are able to see, and helps clinicians in their sort of decision making.
I have a question. What's the highest value of the QIDS score?
The highest value of the QIDS score is about 30.
30, okay.
Yeah.
Why did you cut it off at 9 for the transition?
So that was sort of a clinician-driven decision. So we thought that anything above 9 would be, it was arbitrary in that sense. We could take any of those. But the clinicians sort of informed us that actually having that sort of level puts somebody into a high risk of an episode of bipolar episode of mania or depression.
Anything higher than 9?
Yeah, that was their sort of, that was, yeah, okay. Yeah. Hey.
How sensitive is your analysis to that threshold? Have you done?
We have. It's not that sensitive, but you can determine, you could change the threshold, and it doesn't make that much difference to identify. What you want to be able to do is you want to classify patients into those that are low risk and those that are high risk. And you can have 2, or you can have 3, or you can have 4. And it's just that actually, this sort of approach allows us to be able to identify just some patterns that we can use this simple math to actually get to things where we can see differences, rather than things that might look like this, that might be actually quite hard to sort of identify what a successful outcome could be. So these just give us but you're right, we could the sensitivity of these is important, and deciding what that might be might also be driven by individual patient variation as well. So you might, we've just chosen one for everybody. I mean, this person in particular, it may be better to actually think in a much more more finer way what the right sort of way to sort of separate their scores with. But you just want to make it a little bit more useful than just having this huge longitudinal data. So on the aggregate level, just summarizing this a little bit, we can sort of use these time series approaches to understand mood fluctuations, and we can think about developing maximum sort of like supervised machine learning methods for this, and using algorithms to deal with the missing values. And at a patient level, we can use these very simple stochastic models as tools for analysis and thinking about treatment and the success of treatment interventions. So that's sort of very descriptive, and I want to get into sort of like a little bit about the sort of the way in which we start to think about mechanism, drilling down that sort of hierarchy and thinking about how can we then sort of relate what's happening at one level to another level. I'm going to start by sort of like thinking about relaxation oscillators. They're a nice way in which a nice sort of mathematical tool that helps us to build frameworks to do this. So I'm going to think that mood fluctuations are driven by things that are sort of on the average. So all the sorts of things that Daniel was talking about yesterday, I feel would fit into this. And then we've got things that are, say, two, could be more, unknown processes. And we can so mood is going to be made up in this sense of just these linear components. They won't necessarily be linear, but I'm just going to explain them as linear. Something to do with mood on the average, and something to do with these two processes. So what I can do with that is to write out how mood would change over time as a function of this average mood and these sorts of two processes. And it turns out that actually a very simple sort of total derivative gives me that the change in mood is given by what's on the average, this change over time, the sort of gradient of mood on this process and mood on this process, and then whatever the dynamics of this particular underlying process might be. And that gives us a really nice framework in which to be able to sort of take sort of mood information and sort of step down into sort of like parameterizing what these particular processes might be.
How do we know it's linear?
We don't.
assumption.
But it's just an assumption, right? And it's a nice way in which to sort of like, it doesn't have to be, but it makes the maths nice at the moment. And it makes us, but it doesn't have to be. And we could, and I'll get into that, they may not be linear, because what we can also do is that we can couple processes together. We can add noise to these processes. That's probably on the next, oh no, not on the next slide. But yes, I'll get to that one in a moment. Okay, so we can do that. So what we want to do is we want to choose particular frameworks that might help us in this being able to describe what these particular processes were, what these processes actually are. And we can take a relaxation oscillator, Van der Pol oscillator, written out as two ordinary differential equations, and we can find its steady states. And we can find out when those steady states are stable, and we can do lots of very cool things. And that's all well known. That's not new at all. It's all well known. And these sorts of things, the thing about relaxation oscillators is that you spend a long time in a state and you relax very quickly to a different state. And that's really cool for the sorts of things that we think about, that when we might describe what those states might actually be. And we may actually put psychological the definitions on that, but we're just thinking of us, or neuronal definitions on those, but we're just thinking of those as states at the moment. So what we can do is that, getting to the question about whether they're linear or not. So here's the Van der Pol oscillator where we can show that it's stable. There actually isn't always cyclic. There are sort of parameter combinations where that system is stable. And there's two of them basically, a blue and sort of a red oscillator. And then we can add some. Then we can sort of think about, well, we can couple those together. We can weakly couple those two oscillators, and we can add noise to those two oscillators, and we can use that to start to understand the dynamics. So here's this oscillator where we've coupled them together and we've added a little bit of noise, and we've sort of driven noise-induced instability into this system. The system's stable in a deterministic sense. But as soon as we put some noise into that, we've actually driven it into some sort of oscillatory fashion. And these sort of things just
Oscillator size. The oscillator size. What do you mean by that? The y-axis.
just the sort of like
Amplitude.
the amplitude. Yeah. Sorry. Yeah. Yeah. So these just tell us about the sort of like the instabilities. Sort of a measure of the instabilities in those oscillators. So it's really, so we can do these. We can take this idea that they're not necessarily linear, we can couple them together, and we can make them noisy. So we want to take my framework again, my statistical framework. So we've introduced this is the threshold autoregressive model with these sort of patient data from that true color system where there's all of those nice longitudinal time series. We've got our likelihood structure again, so we'll start off with a linear model. So this is a QIDS score, and this just illustrates that actually we do look, when we look at a host of patients, so there are 42 in the study that we looked at. Here's just examples of the structures to the time series that we see. So there's some patients where they have single autoregressive explanations to their time series, so numbers in the QIDS score now is only determined by QIDS score in the last time step. Threshold autoregressive, so splitting it, that so the different things happening on different up and above and below an average QIDS score based on one time step back, 2 time steps back, or thresholds 2 steps below, above and below a mean. So there's lots of explanation, lots of sort of really sort of rich dynamical information in these sorts of time series. But we want to sort of take that model, so that was my linear model, and I don't believe that linear models describe the world. I think the world is a completely non-linear place. We want to be able to take this likelihood structure and fit my Van der Pol oscillator to those time series. So I'm going to take mood data, and what I want to do is make inference about those underlying processes. Let's call them brain oscillation processes, given in the context of what we were talking about over the last few days. I want to be able to make inference on that. So we're modeling a parameter in this likelihood, particularly in this case the mean. I'm integrating this between the census intervals, so how often people are reporting their mood. And I want parameters for the things, this alpha, the strength of this oscillator, the strength of this oscillator, the strength of the coupling. So yes, they may be parameter rich, but they give us, given the length of the time series and the replication, that we have lots of realizations of a stochastic process from these patients. We can fit these sorts of models to the time series. And here's an example. Here's some examples from that. So we had a study, in this study, 42 patients, as I said. This is their QIDS score. This is what they look like. Some of the missing values, so a large range. So this is what the underlying oscillators that when we fit that model to these time series look like. So they're all very different. And there's the sort of predictions, those one step ahead predictions about how good those models are at describing those time series. What we can also do then is to actually challenge us. So we've got parameters associated with the first oscillator and the second oscillator, and we can ask, given the stability conditions about those oscillators, we can decide whether are they both unstable, is one or the other unstable, or are they both stable. And so these are the sort of like 19 patients that we were able to do this on. It turns out that most of them have unstable oscillators. So that underlying those dynamics are unstable relaxation oscillators. And the other thing that actually, as I said, we can couple them. Turns out that actually both are unstable, and both of those, and the best description of the time series is when those oscillators are uncoupled. And what we can also do, quite coolly, is, I think this is really cool, and it goes back to some of the things that have been said over the last few days, we can understand the individual patient variation. Because we can fit these models at an individual level, we can take the likelihood, we can actually explain what this gamma distribution looks like for each individual patient. So you can have some patients that have the expected probability in their QIDS score, in their mood scores, is going to be at the high range. You can have people with some intermediate scores and people with lots of low scores. So we can use these models not only to describe the underlying dynamics, but we can also use the model to say what have we not explained and what does that actually look like and how bad is it that we've not explained what we've not explained, and where does it sit in probability space, and where does it matter and why does it matter. So again, we can use these oscillators to get a robust way to scale from mood. So we're just using mood data and we're getting down to lower levels of organization. And these stochastic versions allow us to get into highlighting what I like the idiosyncrasies of individual people in these models, in these studies. So I want to take you to some new stuff, and I want to and I really appreciate any feedback you have on this, because what we're trying to do is we're working our way down this hierarchy. We've got mood, and we don't have. Well, I know you guys do, but we don't have access to EEG data, essentially. So we want to just take our mood data and make inferences on things that are happening in the brain as we step down through this. This is my mood model, and as I explained, we can think about this linear. We can think about these processes being not necessarily linearly related, but these parameters, alpha, the beta, and gamma, are scaling the strength of those oscillators. And that's what we want to sort of be able to step down into that. We want to sort of take a sort of multi-scale approach to this. And we can describe those processes, as I said, with this Van der Pol oscillator. We can describe other processes, lower level processes with sort of collective neuron dynamics. So as it was introduced the other day, Wilson and Cowan in the 1970s thought about how we can have excitatory and inhibitory models for describing collective neuron dynamics. And what we want to be able to do is to use this sort of framework within that sort of mood model to be able to sort of take mood data and make some sort of inferences on this sort of relaxation, on these sorts of EI type mechanisms that may be happening. But we've got to think about how to do that. And that's a really hard problem. And we've heard that's a really hard problem. And I don't think we've got anywhere close to it, but this is the way that we've started to think about doing this. And it's important to think that actually we have time, we're measuring time on different scales. So neurons firing on milliseconds, mood changing on some longer time scale. And we've got to separate out those temporal scales. So we want to think that actually there may be n iterations of neuron dynamics, each lasting delta t within a mood time between a mood score. And then if we can do that, if we can define that actually within this mood time, there are n times these delta t neuron events, then we can get to a way of writing out a simple multiscale model. So this is now just using a finite difference expression, so numbers now different from the numbers in the score now versus a score in the last time step is made up of some whatever the dynamics are that we care about. Wilson-Cowan, Van der Pol oscillator, whatever it is. And with a second order, we can take this out to multiple orders. We can just Taylor expand this out to second or third or fourth order. And that's really important because it allows us not to just average over the dynamics. The classic way to do this would be to average over the fast dynamics, for me to average over those neuron dynamics and average over my oscillator dynamics and just put them into, as a slope term, into a linear regression model. But by doing that, by averaging over that, I've collapsed over all of that information, all of that cool information I could get out of my time series. So we don't average over fast dynamics. They can take simple sort of different finite difference expressions to be able to write out a way of linking things that are operating on different temporal scales. Here's some maths that just takes us from that. So I can actually, what I want is I want to be able to sort of like take whatever that oscillatory system is and scale it up. So I need to know what its value is. I can do that. I can replace my delta t term with actually just the ratio between whatever the mood time is over the number of times I think my neuron dynamics are firing over, and I can use some standard or non-standard numerical methods to actually solve this. Model, so that I have a value each point in time of what the neuron dynamics are being. What each point in mood time, what the neuron dynamics are doing. I am not averaging over those neuron dynamics. I'm scaling them with a small time delay approximation. And what I get is something like this. This is the Van der Pol oscillator. It looks like, so this is just in sort of 2D phase space. It starts here and it gets into a nice oscillatory loop. That's given by the maths behind that is just giving this sort of dynamic. And I lay over on top of that the sort of like a second oscillator, so a Wilson-Cowan type oscillator. And instead of having smooth oscillations now, I have something that's really noisy. So I have a method, and we haven't taken that any further. I would really be grateful from this group for any feedback on that, on this method. But we now have a method in which we can take mood numbers, mood scores, and we can infer something at some lower level without actually recourse to having, I know there's cool data out there on this, but without recourse to that sort of brain oscillation data, we can start to get at some pretty cool understanding of how mood and neurons interact, which will be super exciting. Okay, so in the last sort of 10 minutes or so, I just want to sort of step you through some of the more recent stuff. Again, this is all new, and again, appreciate any feedback from this group on the sorts of things. So mechanism of cognition 2, we're interested in PTSD and trauma. Emily in particular, and a group in Sweden are interested in this. So the idea is sort of like the paradigm is that individuals experience some trauma. And rather than, so precursor to PTSD is that individuals experience intrusive memories. So memories that sort of, or thoughts or smells or sounds that just intrude into the mind unexpectedly at unanticipated points of your life or day. So paradigm, nasty see or experience nasty car accident, end up with flashbacks of that car accident, and if that's not dealt with, then there's expectation that those intrusive memories lead to PTSD. So Emily and her team have been developing ways, so imagery-based ways, of being able to intervene in those in dealing with those intrusive memories. So experience car crash, and you might do something immediately after that car crash, before that memory consolidates into an intrusive memory. Or you've experienced some trauma at some previous point in time. You can reactivate that nasty memory and do something, intervene in that to actually consolidate it into an ice cream memory rather than a road traffic accident memory. And the intervention that Emily her team use is this, and it is this: it's playing Tetris. Playing Tetris, using an intense spatio-visual game to interfere with those trauma memories. And that's been well worked. It was Emily and her team showed that well worked was in a sort of lab paradigm, in a lab study, was a really great way to reduce the number of intrusive memories. And over the last few years, we're taking it out into sort of more sort of realistic settings. This is a piece of work we did a couple of years ago. It was on people who had experienced road traffic accidents in Oxford, presenting at the emergency room, and the research nurses there worked really hard at sort of like thinking about how, asking patients if they would be involved in this particular study. And the idea was that you could have standard treatment, and being British, we give them a cup of tea, and all involving this sort of cognitive task, essentially, which involved them asking if they would play Tetris for a small amount of time immediately after this road traffic accident. And what these are the sort of probability distributions of the number of intrusive memories. And the way that those intrusive memories were, people were self-reported. Patients would then, over the next week or so, in a diary, keep the times of which those memories just intruded into the mind unexpectedly. And what we're interested in knowing is that does playing Tetris actually affect the number or the probability of having no intrusive memories? As I said, it worked well in the lab. We've demonstrated that it works well in the field. So note there's differences on the scales here. There's differences on the number of intrusive memories if you just have the cup of tea or you play the Tetris, essentially. So actually, this sort of lots of probability mass are centered around zero intrusions when you play Tetris compared if you just have the cup of tea. So that's sort of proof of concept, well, more proof of concept that this works, and it's been used in difficult childbirth, and more recently, Emily and her team have been using these sorts of methods for dealing with refugees in Sweden.
Was the variation measured there? That is, how significant those results are?
This is a probability density map. So it just tells me what's the probability of having zero. So this is a probability measure.
But do you have some measure of goodness of fit?
Yes. Yeah, but not in these pictures. But these are just telling me what's across this group of patients, what's the expected probability of having zero intrusions. But for each individual,
how many patients were there?
About 80. Yeah, so we do in the paper we have the sort of regression analysis that do all of this. And what we're fitting here are zero inflated Bonsall models. So we fit that. So a zero inflated Bonsall model tells me that. So I might expect that these intrusive memories, because they're discrete, 0, 1, 2, 3, 4, would be Poisson distributed. But they're not. There are a lot more zero inflation. There's a lot more zeros than I expect in these sorts of models. So taking the right statistical approach and determining the goodness of fit and the significance of those tells me there's a difference between people who have a cup of tea and people who have played Tetris in the number of zero. When I control for the fact there are more zeros than I expect, when I play Tetris, there's a higher probability of having fewer or no intrusive memories.
How long did the patients have to report?
A week. Yeah. And another study, again, just sort of like, sorry, these slides are not great. So total number of intrusions. So we've just done a study, it's just in press now, looking at how sleep and intrusive memories interact, basically. So again, this is again in road traffic accident patients. How does the amount of sleep you have and the number of intrusive memories interact? So the red dots on this are patients that went off presented as PTSD patients, and obviously the expectation might be that if we're able to understand these, we may be able to sort of think about where patients how intrusive memories and PTSD might be related. So total number of intrusions against the duration of sleep on the first night, measured by a diary, but also they had wearables as well. So this is just on the diary data. And then the difference, so the fact is that obviously we're all very different, and we heard yesterday about our circadian rhythms and how they're all very different. So the difference in the sleep before the trauma and the sleep on the first night after the road traffic accident. And it turns out there's actually sort of like to minimize the amount of intrusive memories, there's some interesting interaction between the amount of sleep that you have and if you're able to sort of maintain the amount your sleep pattern compared to having something very different, something shorter or longer after the trauma, minimizes the number of intrusive memories that you might see. So they just are sort of like illustrations of sort of how we can sort of use this sort of imagery-based interventions in understanding trauma memory. Well, my approach is, and I'll finish very soon, is just to sort of think about how we might describe this mathematically. So we can describe this again as a sort of Markov chain. So we start with some trauma state, and we're thinking about how we can understand the memory, what happens to those memories after you experience trauma. And you can either consolidate into an intrusive memory, or they can consolidate into a neutral task memory, that ice cream picture. But in order to get from here to here, we have to reactivate them, and we have to sort of like reactivate that memory and then reconsolidate it into an alternative form. So we can think of those as having probabilities. There's a probability of a memory consolidating and being nasty. There's a probability of being able to reactivate it. There's a probability of it entering into this nice state. So we can describe it as a Markov chain. We can think of these as absorbing states. If you get there, you might not get out. I mean, that might not be right, but we have other frameworks that we might think about doing this. So if we can sort of, I'll get into why we want to do this, because one of the things is in reactivating memories, you actually have to give a little bit of a cue. And the strength of that cue can matter. So how strong is the re-experience of the trauma that you've had, and in putting these memories back into this labile state. And once they're in that labile state, then how can we interfere with them? What is the strength of the task that patients experience to actually put them into a neutral memory state? So this is sort of like the reminder. So this is just sort of like, again, we can do them, all the machinery that underpins Markov chains we can use here essentially. So it's a probability of staying in the labile state. So being able to reactivate a memory and holding it in that labile state so you can do something with it as a sort of function of the strength of that reminder cue, that sort of re-experience. And there's sort of like, so we want to be able to hold it in that state. So these are the expected times of memories being in those states. That's what the colors represent. So sort of like a three-dimensional graph here. So basically being able to hold memory, so having strong reactivation cues, putting memories into that labile state. And we can also sort of look at the variance in that, basically. So like what's the sort of like variance of keeping memories in that state? And it really, again, depends on the strength of this. So weak reactivation cues sort of like mean that sometimes memories are in a long state, sometimes they're in a short state. We can get into some maths. In the interest of time, I'll skip over it, but there's some very cool maths using inequalities that we can use to actually think about how long do memories stay mixed. And in Markov chains, eigenvalues, so looking at the differences between the dominant and the second eigenvalue tells us about what's called the spectral gap. And we can measure relaxation times. How long is it before memories relax into a state? This sort of method, this sort of idea, the spectral gap, and being able to measure spectral gap is critically important in all our MCMC algorithms. So how fast does it take for our chains in our Bayesian sort of analysis to converge? So these sorts of things are really, really, really important in defining and describing algorithms for MCMC methods. But here we're thinking about how, in terms of this relaxation time, how long is it before memories relax into an absorbed state, and we're thinking about how long does it take them to absorb into a neutral memory state. We can use this Cauchy-Schwarz inequality, saying I've got my transition matrix now, I know what my absorbing state is, and I want how long is it that do they stay mixed? How long is there a difference between my transition matrix and my absorbing state as I move through time? And this method allows us to do that. We get out some pretty cool math that tells me that the square of the products must be less than the product of the squares for memories to stay mixed. Great, Mike, well done. That's a math result. Not really particularly interesting, but this is more interesting. So basically, if we can put that against some of the parameters that we can measure, probability of staying in the labile state, relaxation time. So this is the bound. We could say how fast. We can't get memories to consolidate into an absorbing state any faster than this. The blue, we can't get down here. It's bounded because it's a stochastic process. It has to step through all of those different things. But actually, more importantly than that, that this has some, I think, translational benefits, because actually being able to keep memories in a labile state and being able to reactivate them involves some sort of intervention. It involves us having to do something. And obviously we'd like to be down here. We'd like to be able to basically, the relaxation time into those nice states to be as fast as possible. But that actually might not be feasible, and what we can do is we might be able to find something that's good enough. We might be able to find an optimum amount of intervention that actually is able to give us translational benefit. And it may be just good enough rather than perfect. So looking for optimal conditions in which we can do these sorts of interventions would be pretty cool. All right. So I've shown that we can use sort of computational and mood and maths to do mathematical methods to do mood maths. I've sort of talked about mood time statistical approaches and how we can use sort of like inferential statistics together with clever hypothesis testing to identify patterns in time series. I've introduced you the idea of relaxation oscillators and how we don't want to average over fast dynamics, and we want to be able to think about appropriate ways of scaling, and the last bit of using these discrete stochastic processes to think about trauma memory and interventions. And with that, I'll stop. Thank you very much.